In this next video, now that we know something about predicting the ways that unlike molecules interact with each other, we want to introduce the concept of like dissolves like and relate that to what happens when I mix two substances together. And so the general category that you want to have in your head is the idea of combining two substances. It could be a solid solute with a liquid solvent, or it could be a liquid with another liquid. But either way, there's three outcomes that we could get. First off, a solid that is mixed with a liquid could end up with a solid layer on the bottom. The solute is insoluble because we don't mix in and it just sets down on the bottom. A good example might be cornstarch in water. If you've ever used cornstarch at home, you'd notice that it does not mix in very well at all. And that's a solid that does not mix into water. So it's an insoluble solid. On the other hand, if I mix two liquids together, I can get layers. And a good example of this, of course, is the classic oil and water. If you've ever mixed vegetable oil with water, you notice that the water sits on the bottom and then the globby, fatty vegetable oil floats on the top because it's less dense. That means that your two liquids are what we call immiscible. So you want to know what the words insoluble and immiscible mean and when they apply. Of course, the third outcome for both of these is that we can form a homogeneous mixture. The solute is completely the solid solute is completely soluble in water and totally mixes in, or the two liquids are completely miscible. Good examples, right? Salt water. You know that up to a point when you pour salt in water and you stir it in, it looks like nothing is there, right? The salt has completely dissolved. Or sugar in water is another option, right? That's another solid that dissolves in water. Or liquids that dissolve are things like ethanol in water. So grain alcohol, right? All alcohols are not 100% alcohol. It's mostly water with small amounts or larger amounts, depending on the proof count, of ethanol mixed in. But those are our three outcomes: an insoluble solute, two immiscible liquids, or a homogeneous solution where it looks like one consistent mixture. This up here is just air, just so that you're aware. And how do we decide? The principle's easy. It's called like dissolves like, right? It says that I make a homogeneous solution. So remember, that was our center outcome. I get a homogeneous solution. I get perfect mixing when my components have favorable interactions. And by interactions, I mean intermolecular forces. So let's think about what's favorable. If two compounds have London together, that's favorable. If they have dipole, that's favorable. If they hydrogen bond, that's favorable. And ion dipole is also favorable. And what do you know about London? London is a nonpolar molecule with another nonpolar molecule. And what do you know about the rest of these? This is something polar with another polar molecule or an ion. Things that aren't charged, things that are nonpolar, like to stay together. Things that have charges, either full charges by being an ion or partial charges by being a polar molecule, like to stay together. Like dissolves like. On the other hand, unfavorable. Well, that's dipole induced dipole, or ion induced dipole, right? You put a polar thing with a nonpolar thing, it doesn't like it. It's unfavorable. You put an ion with a nonpolar thing, it doesn't like it. Nonpolar things like to stick with other nonpolar things. Polar things like to stick with ions. Like dissolves like. Right? The basic rule is that, right, like compounds stick together. right? They mix or form solutions. Unlike, don't. And how do I decide? Based on polarity. Non-polar things stick together, polar things stick together, and with ions. And the reason for that is that these favorable interactions that happen between the two components of the mixture are as strong as or stronger than the pure substances. So when I put benzene and toluene together, these are both nonpolar compounds, and the interaction between benzene and toluene is strong enough to make the benzenes and toluenes want to hang out together. On the other hand, if I put benzene, nonpolar benzene, with polar water, that interaction is dipole-induced dipole. It's an unfavorable interaction. Water doesn't want to be anywhere near benzene, and so they split up into two layers. Let's use that to make some predictions. So let's go back to our original compounds from the other day. We're mixing together pairs of compounds, and we're predicting what will happen. And in each one, what are we going to assume? That the left is the solute and the right is the solvent. Remember, solute just means that there's less of it and more of the other. Or, sorry, this should be solvent, right? And you can also assume that all the solvents are liquids. So I'm mixing a liquid and a liquid and a liquid and a liquid. Your next goal is to decide whether it's a solid or a liquid. And I'll tell you right now on this slide, ionic equals solid, and then covalent equals liquid. Because remember, we had to decide between three outcomes. Outcome one was insoluble solid. Outcome two was two immiscible liquids. And outcome three was homogeneous solution. So let's make our predictions. And again, we'll move from right to or left to right and top to bottom. And let's see what happens. I'll reveal them one at a time. So pause and give it a try. So in this first example, remember I said the one on the right was always a liquid solvent. The one on the left was going to depend on whether it was ionic or covalent. So this is liquid water and liquid ethanol. So we already know that our outcome is going to be that they're miscible, they mix together, or they're immiscible, they do not mix together. Since they're both liquid, and since they're both polar, like dissolves like, these two are miscible. Let's move on to sodium chloride with cyclopentadiene. So here's what we know. Sodium chloride is an ionic compound, which makes it a solid. Cyclopentadiene on the right is all carbons and hydrogens, so that has to be a nonpolar compound. What did we decide? Like dissolves like. So ionic things do not like nonpolar things. And so my conclusion is that sodium chloride is insoluble in cyclopentadiene. What would I have? I'd have a test tube with sodium chloride at the bottom and cyclopentadiene on top. Two more. Let's try this next one. All right, this molecule on the left is called ethanol, and because it's a covalent compound, I'm going to mark it as a liquid. This molecule on the right is called toluene, and I'm going to also mark it as a liquid. And I'm going to identify them as a polar compound on the left and a nonpolar compound on the right. Like dissolves like, these are unfavorable interactions, and so I say that these two liquids are immiscible. I would have a test tube, and I'd have two layers. One more. So here we go. Copper 2 nitrate is, of course, an ionic compound, so I'm going to give it a solid phase label. And on the right, ethanol is a liquid and a polar compound, as we've said before. So if I put a polar thing with an ionic thing, I know that those are favorable interactions. And I identify then that solid copper 2 nitrate is soluble in ethanol. I would have one homogeneous solution. So I had two situations where I made a homogeneous solution, and two situations where I had a solid on the bottom or I had two layers of liquids because they did not mix. Being able to predict solution outcomes is important because it's only these miscible soluble ones that go on to do what we're going to talk about in further videos.